Hey, Kayla, how are we doing? Who all we got in the chat? I've got Mubot awake. He's waking up. I was grabbing a quick snack. I grabbed some candy. That's all. I need to eat healthier. I need to take care of myself, eat some real food. I'll eat some real food later. We had pizza last night. Remember last night I was talking about pizza in class. 500 points, Kayla. We're going to start the activity here in a moment. But pizza and candy. I'm just a big child. It's like you ask a 10-year-old, what do you want for dinner? Like, pizza and candy. And you're like, you're going to be a really bad adult. I'm still learning how to adult these days. Some days a pizza and candy day. We'll put the timestamp in here. 310, question 1. And let's do some review. I think we're doing this about at 310 right here. 304. Gonna talk after this. I've got some Seinfeld. Oh, going on. What Seinfeld episode? Let's go to the main screen. Which episode of Seinfeld is it? Put it in the chat right here as we start to talk about the first one right here. This is the activity number 8. We're doing the first question right here, and we are going to make some models right here. Kayla's going to let us know which episode it is. Is it the one where Jerry does the crazy thing, where he's dating someone? It's like every episode. Seinfeld, it plays all day at my house. Season 5. Is that where they're at Del Boca Vista? They're always at Del Boca Vista. I'll have to hear more about it. Okay, so we're going to make a model predicting profit from the 6 predictors in the PL data frame. So this is from the launch data set right here. We are creating our own data set. If you notice, it says launch is not found. That's because we need to load up library reg class probably, and that might fix it, or it might not. Nope. We need to load in. Ooh, what's going on? Oh, we need to load the data set. The dataset launch is a product launch found in the reg class data frame, and it probably tells you all that up there. We have a profit variable where Jerry and Elaine are God. Oh my gosh, I can't remember that one. Wow. I need to rewatch some Seinfeld. So we have here the different X variables, X1, X2, X3, X4, X5, and X6, which represent different things we've collected about the launch of this product. And I believe we're trying to predict the profit of a product. So profit is the Y variable of interest. It says for us to first fit right here a model predicting profit from all 6 variables. What is the shorthand for every single variable? I'll do it the long way right here while someone tells us the shorthand for every variable. Profit tilde x1 plus x2 plus x3 plus, I didn't do a plus there. How do you make the text smaller? Control Shift minus or Control Shift plus. So Control Shift minus or Control minus or Control plus, Control Shift plus and Control minus or Command on a Mac. So I'm trying to find right now the shorthand to do every single X at once. Great job, Sierra. That is correct. Rather than writing out every single X right here by doing X1 plus X2 plus X3, yada, 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 Seinfeld, we can just put a dot. That means all the X's, whatever's in this data frame right here. And good to see you here, Sierra, and Kayla too. We're just going to take profit as the Y and then all the X's. So that just stands for Y variable of interest and all X's. Then we go here to data equals, and we do product launch data frame. Now, don't worry about the do try catch error. That is something to do with the graphics. Don't worry about it. You probably didn't even see it on yours. And now let's take a look at our model. First off, we're going to analyze some of the statistics on this model to see what we have. Really, I'm going to remove this plot, and I'm going to rerun it. There we go. So we need to know what the R squared is. R squared is the amount of what we've explained in profit via our model, which we could probably just say that on the test. Like blank percent of the this in profit has been explained by the X's in our model. Looking for a V word right there. So when we're talking about the amount of what in profit that these products might have, the variation, great job, Sierra, right there. The amount of variation we've explained. So 68.98% of the variation in profit. So let's say here, 68.98% of the variation in profits has been explained by the X's in our model. They're literally X's at this point. Next, we get to the R squared adjusted. Now, R squared adjusted has some key concepts to it, so write these down if you don't have them. Can anyone tell me anything they know about R squared adjusted? Like, we'll talk about what it is right here, but what's this r squared adjusted thing we have? So it is what it says it is. It's r squared that's been adjusted, and it means it's been adjusted for how many variables are in the model. So you can think of it as r squared that's been penalized. The more variables you have in your model, the more penalty it gets. Now, variables are going to help r squared go up, but r squared adjusted's been penalized. So tell me another thing about it. There's a lot of keynotes we should have on it, like key facts about r squared adjusted that we should know. What is, it's always smaller than r. Great answer, Kayla. Always smaller than r. That's just a fact about it. Like, it is always smaller than r, except in the one circumstance when r is 1, because the penalty works off of the unexplained portion, the coefficient of non-determination. Don't worry, I don't put that trick question on the test. Always smaller than r, except when r is 1. But it also can be r squared, did I say? Oh my gosh, Kayla, 500 points correcting Brian right there. I love it. Great work. Do correct those errors. I wrote r. It is r squared. All are smaller than r squared. Good correction. I was like, what? Yes, r squared. So now also we have that r squared adjusted could be negative. Because remember, the smallest value of r squared, I almost did it again. The smallest value of r squared is 0. So if r squared adjusted is always smaller than it, then it could be negative. It also has no real interpretation. It is used for model comparison. So it fairly compares multiple models. Like if you have a model with a lot of variables versus a model with few variables, that's a fair comparison of two different models. So r squared adjusted is a measure we could use to talk about the what significance of a model, not the this significance. The r squared adjusted is a good way to figure out the what of a model, not the statistical significance. R squared adjusted is another metric in our toolbox to analyze the what significance. That one, and that one. Practical, right answer right there. It starts with P, practical significance. So we can look at practical significance with these numbers right here, the typical miss the model makes, the r squared after adjusted for the variables in the model, or the r squared, which is the amount of variation explained by the x's in our model in the y variable of interest. So we need to know what each of these mean. Degrees of freedom are a mathematical thing. Degrees of freedom are a mathematical thing. Well, that's the F statistic, and then this is the numerator and denominator, but we don't work about that. Oh, no, fine, Kayla, don't worry. It's good practice. You're doing great. So that was question 1. I think that's it, right? We just looked at a multiple model. Cool. Okay, let's take a note here for question 2. Good practice, and I do mean this. A lot of the remainder of this course is repetition. You will see a lot of these same concepts, so we really practice the same ideas. We've already talked a lot about r squared adjusted, and RMSE. Oh, I guess the model typically misses the prediction of profit by about, or the actual value of profit by about $0.287, thousands of dollars. I don't know. Maybe it's like an individual product here. How much profit we'll make off of it, like on the sale of it. But the profit prediction is typically off by about this amount, whatever units of the y is. We could put here units of y. So when we are using the RMSE, it's in the y units we typically miss by. Yeah, you could. If this was a test question, I'd want it to be more descriptive. Like as a test question, I would probably not let this pass. I would say if we're going to appeal write this up, we're going to tell you the units of the y. So I don't love that as a test question right now. It would really need to have better context. All data needs context. Like, what are we predicting? So now we are on to question number 2. And question number 2 says, interactions play a key role. This is what we'll be covering next class. Interactions play a key role in many problems. Now, the way an interaction goes, like, what is something, do your kids like bacon, Kayla? I'm guessing one of my examples deals with bacon. So, like, what if you say to your kids, like, we're putting bacon on the pizza? Would your kids be like, yay, or no bacon? What would your kids say? Of course. So we got here bacon. Really good. There's a sausage bacon. If you like, we've been trying that lately. To get some turkey bacon, whatever bacon, or if you're vegan, no bacon. Maybe they got some faux bacon, some fake bacon. Whatever you like, if you like it. If I say to my kids no bacon, I'd be like grounded. Well, check out this. You say to your kids, we're going to have burgers. And your kids say, well, I give that burger a 7 rating. So without bacon, this is the no bacon burger. And then we put on the bacon burger, or let's say no bacon versus bacon. And your kids say, oh my gosh, mom, bacon made it better. So you then say to your kids, oh, it looks like bacon makes everything better. Now remember, this is the burger line. And now we're going to say, okay, well, we got you something that you'll love here. Because you give toothpaste a 3 rating out of 10. We want them to really love the toothpaste. So we're going to put bacon in the toothpaste. A little bit higher on it. Maybe they don't hate toothpaste that much. They say, Mom, our toothpaste is only okay. Our toothpaste has a 5 rating. Kind of close to the no bacon burger. What happens when we put bacon in their toothpaste? Like, let's just say it's actual bacon, not bacon flavor. It's no. So tell me this. What do you notice about these 2 lines, which we're going to notice for our problem with this example? The way in which bacon impacts the what people like, the y variable, whether or not they like it, would depend on the product. Right now they hate it. Bacon toothpaste, they're like, this is ridiculous. The way in which bacon impacts the y variable depends on the product we are putting it in. Would you say that there is a very strong interaction here, Kayla? Would you say there's a very strong interaction where the impact of bacon is very different on these 2 products? And that's what an interaction is when we have an x variable right here, like adding bacon, and then we have the type of product, another x variable, is going to have a very large impact on the y. So let's look at this for our example. Good story. I love doing the bacon one. I actually do a soda lab for this with the honors class when I could do labs. So we did a soda taste test and did like vanilla Coke versus like peach Coke, vanilla Sprite versus peach Sprite. And usually you would think vanilla Coke would do better, but for some reason people like peach Coke. It's like Coca-Cola. Okay. So we want to include all 2-way interactions. I'm going to I'll write it out. We're predicting profit and tilde dot raised to second. So this will include all 2-way interactions right here, and I'll show it. So let's run the summary of it, and then we'll take a look at the answers. So if you see right here, these are the interactions. You can make an interaction by doing simply the following. This is an interaction term. To make an interaction term, let's do interaction test right here. I could simply do x1 colon x2. This, it's not. There we go. This model is a model that only includes what here, Kayla? Can you explain to me the only variable in this model? Yeah, the raised to second includes all interactions. And this new model only includes what right here? It only includes the what interaction. This new model I made only includes the what interaction. So we're just showing an example. This is a model right here. Look at the x variables. It has an intercept and it has the what interaction. How would we, that stands for the what interaction. What does that line mean right there that I've highlighted? This model only includes in it the what interaction between 2 variables. And what are those variables? So the only thing in this model right now is the x1, x2. The only thing in this model right now is the x1, x2 interaction. Does that make sense? This right here stands for the x1, x2 interaction. We'll look more what this is in a moment here. But that says the only variable, that is like a variable. And every variable will always have with it, starts with a C. This is so tiny small. But every variable will always have with it a what. So when we have like an x variable, which this x variable is an interaction variable, it'll have with it a what then? Which is funny. This is kind of like x1, and this is kind of b. This is b1, a coefficient, exactly. So that's the coefficient of the interaction. But now watch this, and this is a key thing we'll be learning right here in this example. Now we don't just have the interaction in the model. So now we don't just have the interaction in the model. What else do we have, Kayla? We don't just have the interaction between x1 and x2. What else do we have in the model? So now we don't just have the interaction in the model. So take a look at what's in the model. So that's what's in the model over there. And we don't just have the interaction in the model. So this would be the intercept. We have the actual x's. We have x1, we have x2, and then we have the interaction between x1 and x2. Now think about this. the interaction is not statistically significant. So I'll show you what this looks like right here by going to see interactions. The interaction right here is not statistically significant, and I want you to take a look at the lines. We'll make it so it looks really nice and big. These lines look kind of what right here? So this is the interaction between x1 and x2, such that as x1 gets larger, profit goes up, but this is when it's at different values of x2, like a small value of x2, a medium value of x2, or a large value of x2. This is x2 increasing profit, so if x2 goes up, profit generally goes up, not like cause and effect. And these are the values of x1 right here and how x2 would differ in its relationship with profit. So what do you notice about these lines for the not significant interaction? Remember, this interaction is really not that significant. They are linear, and the lines themselves kind of go with each other. They're kind of parallel. Well, the relationship these variables have, do you see how x2 is steeper? Like, look at the x2 line right here, and you see how steep it is? x2 actually has a statistically significant relationship with profit, and you can kind of see that right here, and we're looking at this graphic. x1 actually doesn't have a statistically significant interaction. I mean, a statistically significant relationship, and it's very flat almost. But the interaction is pretty interesting, and let me see if I can find one, because I think it's this. Closer. I want to show you one that's really... Yes. Kayla, what do you notice about these lines here? Talk to me about these lines. They don't look so much parallel now. These lines look more what to you? These lines don't look as parallel. They look more this. Not parallel now. They're not parallel, correct? They're more perpendicular. They kind of have more intersection. So now when we look at it, tell me, and be very careful right here, and this is the idea of interactions, which we're learning about right now. Exactly. Great work, 100 points in the chat. So tell me, does x5 increase profit or does x5 decrease profit? And be careful, this is a trick question. Does x5 increase profit or does x5, this is x5 right here, like that line is x5 increasing profit, that line is x5 decreasing profit. Does x5 increase profit or decrease profit? What do you think? And then look at what the interaction is telling us. And this is where hopefully we start to see it. Does x5 increase profit or does it decrease profit? What do you think? And then think about what the interaction thing means. It's a good thinking moment right here. It will decrease it sometimes. x5 decreases profit for large values of x2. When x2 is large, x5 decreases profit. But when x2 is small, x5 increases profit. Would you say that the relationship x5 has with profit depends on x2? So in some instances, x5 has a positive relationship. That's when x2 is small, and that's the small line right there. But when x2 is large, x5 has a negative relationship. And this is because of the what, Kayla? This is because x5 has a what with x2. As in the coefficient of x5 is going to very much what on x2? Very much depend. It has an interaction. Does that make sense? x5 has an interaction with x2, meaning that the way in which x5 explains profit would highly depend on x2. And you can see it via the statistically significant, and great job right there. It depends. That's what we have. And so let's look at the problem we're looking at here. This is a much bigger problem, hence why I wanted to do smaller examples to start. We're not just doing one interaction, we're actually doing all the interactions. So we're just going to go back to doing all the interactions. So now we have all of our x's and all the interactions. Recall the values of all these. Look at the r squared. Okay. So here's our crazy huge model. So r squared, 72.73% of the variation in profit is explained by the x's in the model, or explained by this model. R squared adjusted. Which model is doing better, Kayla, right now? The interaction model or the original model? So here's the original model up here. And we didn't take this. I think it was actually right next to it. It was something like this. Be careful, that's an estimate. 68.87 versus this. The model with interactions is doing better. Does that make sense? The model with interactions is doing better because the R-squared adjusted is higher. The second. And then we can also compare the typical miss, and it's lower. Here's the typical miss here. Here's the typical miss here. I think we can select them both. Yeah, there we go. You just have to select the top one first. The second model, which is seen on the bottom, has a lower typical miss, which says to us that the second model is better. So the second model is doing a better job via R-squared adjusted, which we can use to compare models of different size. Also, we can use the residual standard error. We could also technically, and this is a good review, I'll say the answer, we could do an ANOVA here. What did we call that second model? I think it was mint. So we put it big comma small. And the partial F suggests to us we should use the second model. So the partial F statistic compares. Do we not look at the multiple? Exactly. So when we compare models, we won't look at the multiple R-squared because models with more variables will always have a what R-squared. So if a model has more variables, because our first model just had x1, x2, x3, x4, x5, x6, the second one had all those variables in the interactions. Well, we can talk about that. But when we want to compare models with more x's will always have a what R-squared because that's what R-squared does. We don't want to, in the multiple world, we don't want to compare R-squareds because models with more x's will always have a what? Higher R-squared. So to counteract that, we shouldn't use R-squared when we compare models. We should use R-squared what? Because the more x's you put in, R-squared will just go up. So we can counteract that by saying instead of comparing models with R-squared, which we could still interpret R-squared, instead of comparing two models with R-squared, we could use the R-squared, I think if I have to say it, the R-squared what to compare models, the R-squared adjusted, exactly. So the R-squared adjusted is how we can do a fair comparison between models of different size to put them on an even playing field because it's adjusted for how many variables are in the model. And then we could run a partial F to see if going from the small model to the big model, there is significant variation explained, and that's what that p-value represents to say, going from this model to this model, there is significant variation explained. Good review on partial F right there, compares models of two different size, and lets us see if there's a significant decrease in sum squared error. How many of the 10 interactions are statistically significant? I need to check to see if anyone's getting this wrong because there's more than 10 interactions. I believe there is 15 interactions. To see how many of the interactions are statistically significant, we would view the summary. And in the summary, statistically significant is going to be anything with a star, i.e., this is statistically significant. This is statistically significant. This is not a star. It represents something with a p-value between 0.05, 0.1. I'm so happy. Someone said they didn't know this. We were mentioning this at the end of class, I think, and they said, wait a minute, that's what that represents? And I'm like, yes. The stars represent statistical significance, super statistical significant here, super statistical significant here, statistical significance. You can say super statistical significance or it's just statistical significance. But anything with at least a star, more stars just mean more significant. These values represent right here. Yeah, I know, right? So you can just be like, yes. You can just count them up, but do not count the dots. I tell R to be like, hey, maybe you should stop doing this super statistically. Exactly. It means the p-value was less than 0.00001. 0.001 right there. And between 0.01 and 0.001 are 2 stars. So this one right here is between the two values right here. That's why it has 2 stars. And then 3 stars means less than that, 0.001. So very, very small, like zero-ish. But yeah, quick way to like scan your output to see if you have significance is to look for the stars. Good stuff. Really helpful. Pursue all 10 fitted, peruse all 10 fitted interactions. Peruse. And run the C interactions with the added argument, many equals true. Here we go. Okay. C interactions on our interaction model with many equals true. Now, don't try to knit this. This will cause problems. Tra-la-la-la-la. Okay, so this right here is the interaction starting us off. That is between 1 and 2. This is actually statistically significant. And we do notice there will be some peruse. Notice right here, this is statistically significant. The way in which profit is explained by X2 depends on X1. The weakest interaction for us to see is going to be apparently X3, X6. Let's kind of swing down to that one here. Oh, well, we do have along the way, we did look at 2, 5. So we'll do 2, 5 and 3, 6. 2, 5 should be very perpendicular because the way in which 2 is explaining profit will depend on 5. So let's go to 2, 5 here. 2, 5 is right here, and look at the perpendicular nature of this. It doesn't have to be perfectly perpendicular. Hey, what's up, Thomas? Great to see you here. Let me know if you got questions. So this is showing a pretty significant interaction. The more perpendicular lines are, the stronger the interaction. But I've had people say this is not significant, but then they look at the plot and they say, wait a minute. Oh, wait, that's 2 and 6. Where's 2 and 6? Really? Wow. I'm shocked that it's that perpendicular. Like, even that shocked me. Generally, the weaker the interaction, the less perpendicular. Really? Well, that was way more. This one looks way more perpendicular than I would have thought. But maybe it's standard errors or something. There we go. That's a good example. Definitely this is true, and it just depends on a lot of factors like sample sizes and standard errors. But the more parallel the lines, the weaker the interaction. So a good theoretical test question could simply be, if I draw 2 perfectly perpendicular lines, if this was your output, Kayla, what would be the p-value of the interaction? This is the weakest interaction possible. There's no interaction here. So the weakest interaction possible, this is the weakest, perfectly perpendicular, like 100%, no intersection anywhere. So now the way in which one of our variables explains the y does not depend on another. The p-value would definitely be what? If they were perfectly perpendicular, because the coefficient of the interaction would actually be 0. So if they were perfectly perpendicular, the weakest interaction possible, close, Kayla, it'd be the reverse. It'd be 1, because this is the least significant. So think about this. This is a very strong, significant interaction where the lines are crossing like that, and that is super significant, where the top one, so great work there, Kayla. The top one, and that's why I ask these questions, because I know don't worry, I'll ask it during class, and watch, you'll know the right answer. The top one is a not significant interaction, where the bottom is a super duper crazy significant interaction, because, so the weaker the interaction, i.e. higher p-value, the more what the lines will be. The weaker the interaction, the more what the lines will be. Like this is this one right here, i.e. look at the p-value of it, and then look at the lines. This one definitely follows theoretically what we should see. This has kind of what-ish lines. They don't have to be perfectly this. Look at how weak this is, how not significant. The more parallel. And then when you see significant interactions, they're going to be more perpendicular. They might not look perfectly perpendicular. We saw a great example with 2 and 5 with a super strong. This is the most significant interaction right here on this one, and you see more perpendicular. Everything isn't perfectly described by this, but everything else held the same. It matters on estimates and stuff. This is 4 and 5 right here. So 4, 5, is it significant? What should it be? Oh, it's not. Just barely not. But definitely more parallel lines are weaker interactions. More perpendicular lines are stronger interactions, i.e. more significant. Good stuff right there. Good review. Fit a model predicting. Did we do? Look to have a strong interaction. Look to have a weak non-existent. So in the model, by running the directions, we did that right there. Good deal. And now fit a model predicting profit from X2 and X5, their interaction. So let's run this right here. Let's call it MD. And we're going to fit a linear model predicting profit from the X2, X5, and their interaction. Now, I want to point something out right here. When you do the star, you carry what's called model hierarchy. So model hierarchy is if you include the interaction, you will include the terms themselves. Model hierarchy states for interactions, if you have the interaction in the model, you will include the terms themselves. And this is done with the star. To what is called violate model hierarchy or not carry through model hierarchy is to do the colon right here. And then you will see we do not get the X2, X5 term. Can we be touching... we could say less parallel. So if they're perfectly parallel, the p-value will be 1. And then the p-value starts to decrease the less parallel they are. Does that make sense, Kayla? So if they're perfectly parallel, that is the instance when the p-value would be 1. But if they're like this, the p-value might be like 7 or something. The more perpendicular they are, the more non-parallel they are, the lower the p-value. So the only theoretical one I could ask people on the test, because you wouldn't be able to theoretically know the answers, would be ones with perfectly parallel or ones that are like 100% perpendicular. I guess this one doesn't, I don't know, this one would be a worse theory question, but that one has to be one. If they're perfectly parallel, there is no interaction. The interaction has no impact on the model, i.e. it is not significant. Seeing like the reflection in the window. But does that make sense? Perfectly parallel, weakest possible interaction, i.e. not statistically significant. Here, we'll take a look at this one. Well, sadly, we can see the interaction. No! So I think it is significant. And let's run the visualize model on this, and let's take a look at it. Visualize model. Okay. What do you notice about these lines? They're pretty not parallel, right? And if we look at the summary of it, we can look at the values in it, and the interaction is significant. So that means the way in which X2 explains profit depends on X5. For very small values of X5, X2 has a super strong relationship, the blue line right here. For larger values of X5, X2 has a weaker relationship. It doesn't change sign, but over here we see X5 actually really depends on X2, because for small values of X2, X5 has a positive relationship. Great job. You got to look at the graphics line and be like, okay, wait a minute. For small values of X2, that's the blue line, X5 has a positive relationship. For large values of X2, X5 has a negative relationship. So the way in which X5 and X2 explain profit would depend on the other variable, i.e. this whole thing, interaction thing over here. And so let's look. I think it probably wants us to write out the equation. If it doesn't, I'm actually going to write it out. Look at the plot, which show the relationship. I think we just explained that. Let me do this, and this is going to be a big thing. I think this is on the homework. Let's put how to write implicit lines. Okay, let's talk about how to write the implicit lines right here, which is a thing people often don't know how to do. When I say implicit lines, I'm talking about these lines right here. Imagine, here we'll do a different example because I don't like no wonder we didn't ask. These are decimals. Nah, it's so small. I don't like that. Okay. I'm going to do my own example right here and talk about how to write an implicit line, which is on the assignment. So now, the way in which somebody's weight might explain, probably not going to be significant, somebody's height might depend on their GPA. Let's see if it's significant. It's probably not going to be. Close enough. Okay, so now we're going to write out the implicit lines. Questions on the test or on the homework assignments say things like, write out the implicit line for someone with a GPA of 2.0. So if you got this on the test, Kayla, do you think you could solve this right now? Just this question where it says, write the implicit line for someone with a GPA of 2.0. And I'm hoping after we do this example, it'll be like, got this. Because right now we need to know that the implicit lines are just a solved line. So if we say the implicit line, it's just we plug in values and solve the line. Well, here we go. Check this out. How we do it first is write the original equation first. And this is what we've been doing all along right here. To write the original equation, this lets me do LaTeX writing, or it should. There we go. This lets me do like notation or mathematical writing. I'm going to do predicted height. So height is equal to what? What is the first thing you think I should add to this equation, Kayla? What is the first thing? We're going to write the full equation first. What is the first thing you think I should add to this equation? Remember our trick for writing out the equations? It's like this plus this times this plus this times this plus this times this plus this times this. I know, I like it. Paul calls LaTeX or LaTeX. What's the first thing we should add to this? If I say it, you'll know it, and I bet you're like, wait a minute. More points in the chat. What do you think we should add to this first? What's the first thing we add to our equations when we write them? Just think regression. Just think, I'm just writing a regression equation. The first thing we should add is what? Not your question, I promise. We're just going to add the what? We're going to write the regression equation right now. And the first thing we should add is, close. Not that yet. Not you're on the right track. That's B1. Oh, yeah. I'll write that. You can do that. Zero. Good work. This is correct. Nothing's wrong yet. But we're missing something I would generally put before it. Yeah, you're on the right track, though. This is right. Intercept. Yep, let's put the intercept. Great job, Caleb. Yep. See, I told you. I was like, you got this. So we're going to do the intercept. There's the intercept. And then what do you think I should write next? What's the next things I should put in here? What should I write next? Remember, it's this plus this times this. Look, Caleb, you got this. And then we'll times that by GPA. Exactly. And then you say, well, wait a minute. What do I do now? Well, let's do the same thing. Plus this. And then let's grab the interaction. And although it doesn't say it, what do you think we should do to these two variables right here? What do you think that implies with that colon right there? I promise it's nothing crazy that we haven't. You've seen this in mathematics before. It's nothing new. What do you think it represents when we have like this and this, how they're interacting? They're going to what each other together. They're going to what by each other. And I'll tell you one of my favorite questions right on the test. I'll write it next year. So what do you think I remove that colon right there, and what do you think I'll put in place of it? So instead of writing a colon, we'd write what? Boop. Just multiply. They're going to work together to solve the equation. And then, great job, Sierra, right there. Excellent work, Sierra. And then, when it says write out the implicit equation for someone with a 2.0 GPA, what do you think we should do right here to start writing the implicit equation for someone with a 2.0 GPA? Just kind of think like, okay, if I want to write this equation, I know Sierra doing a great job right there. If I want to write this equation for someone with a 2.0 GPA, what do you think I would do? So if I want to write this equation for someone with a 2.0 GPA, just think like if I said, write out the implicit line for someone with a 2.0 GPA, well, now that we've written the full equation, you got it, Kayla. That's it. We're just going to go right here and go 2, 2. And look at this. This value right here is a constant, which will change the intercept, and this will change the coefficient of the slope. Wait a minute. That's what the interaction does. The interaction literally changes the coefficient of the slope. And that's what this is doing right here, the interaction term to the x variable weight. It's changing the coefficient of weight. Does that make sense, like seeing it equation-wise? That the intercept, cool, the intercept's going to change, but the slope right here is changing via this right here. So now we're going to take and just kind of reduce. Here we go right here, grab the equation. We'll add this to the intercept, or subtract rather. So 2 times 1.84. And we'll subtract that from 62.06 minus this. There's the new intercept. New intercept. That's been subtracted off. And now we're going to take and times 2 times the interaction term times 0.0114. And then right here, we're going to add that to the coefficient of weight. There we go. And that's the new coefficient. And there it is. There is the line for somebody with a GPA of 2. This is the implicit line. And that's what's going on over here. It's solving values. But the easiest one to ask is solve the line for somebody with a GPA of 0. So just take a moment and solve the line for somebody with a GPA of 0. Let's change the question right here. Whenever I put a question like that on the test, I'm like, oh, please know how to do this. Life will be really easy. Just think about what happens. Just start plugging in numbers in your head and being like, okay, if I solve this out for someone with a GPA of 0, what would happen here? Start plugging in and being like, well, that would go away. That would go away. Well, then the equation would just be this. Start plugging in values. Remember, times by 0 does something. Write the implicit line for someone with a GPA 0. Get a second more. Good practice right here if you can do this. Well, wait. So what you want to do, Kayla? Plug in a 0 here. Sierra, great job. Yep. And take a look. Does that make sense, Sierra, right there? I mean, Kayla right there? Is if we plug in 0 for someone's GPA, the line would solve out to height equals to 62.06 plus 0.038 weight, because these are just going to, as Rock knows, it doesn't matter. Those will just... Oh, you plugged in 0 for weight. Yeah. Yeah, no, you'll plug in 0 for GPA and solve the implicit line for somebody with a GPA of 0. And then you can solve different lines. And that's what's being drawn for here, is it's literally plugging in values. And that's what you're seeing with the implicit lines. But good practice. We could put the GPA back here. Oops. Is this making sense how to solve implicit lines? It's just writing the equation and then plugging in the value it tells you to. So the steps for solving an implicit line are write the equation, plug in the value, and then just reduce. So hopefully, I love the questions on the test because I'm like, okay, write the equation, this plus this plus this times this plus this times this, plug in the values, and then it's algebra. So good stuff right there. How did it? I love it. I love it. I love it. All right. So let's look at finding outliers and influence points even with 5 predictors. Which we're using the influence. Okay. Sorry, buddy. Okay. Question 4. Did we do question 3? There's no question 3. Awesome. Question 4. Question 4. Okay. This, Kayla, it is time for some really great review right here, because now we're on to the influence plot. And the influence plot is going to let us see if there's influential points. And are there influential points? Yes or no? Quite simply put, I'll disappear so you can see it. Are there influential points in this model? Are there influential points? Now, I'll decipher the graphic for you as we look at this. The deleted studentized residual, in basics terms, is a measure of how far something is away from the model. Great job, Sierra, right there. So these points right here are a lot further from the model. Please review the notes on deleted means the point is removed from being influencing the model. Studentized means it's been standardized, and residual means we find its distance. It is kind of a residual. It's a very special kind of residual, so don't just say it's a residual, but it is a type of residual that is true. So this is how much the model misses it by, and calculated a very specific way. Now, the reason we standardize it is so that we don't have to worry about the units of the y. So the reason it's standardized or studentized, which means to a student t, is we have to say, well, we missed by 80. Now it's just that the t-score, because studentized, is more than 2 or -2 outside of absolute. So these are the extremes when something is very far away in terms of y. But then we have to know the second term on the bottom here, which is called leverage. Leverage is how far are you away from the mean of the x's. So if you notice where it's on the x-axis. And then this one's on the y, which is a terms of a unit of measurement of how far we are away on the y. And then across here on the x-axis. So for something to be influential, it has to be large on both. It has to have high leverage, which is beyond this point right here. And it also has to have an extreme deleted studentized residual, which is outside of 2 or -2. And so the only points that do this, I say only, but there's quite a few, point in row 66, 90, 97, 250, 275, 461, 463, 471, and 617. I wish it put the number right here. I might be able to recode it. Shouldn't do it right now. It'd probably take me 5-10 if that. But I wish it showed the number. And actually, I think there's a way. Let me see something. I don't know if this will do it. Let's see. Really? I don't know about the way they're plotting influence. 66 has the most leverage. So that's 0.66, which showed up here. That point with the most leverage is 66. This is not Dr. Petrie's graphic right here, but Dr. Petrie graphs it this way, and the default R graph is this way. They are indicating that is a high leverage point. If you notice, we can see influential must have high leverage and high deleted. Exactly. And by high, we mean in terms of absolute value, like is -3. So Kayla, is -3 deleted studentized residual high? Like, is that large? Is a -3 deleted studentized residual large or high? So would -3 deleted studentized residual be large, i.e. high? If you know the answer to that, you're good. Would -3 be large? Yes. Anything outside of this bounds, this is like the normal bounds, because we're actually doing the normal techniques right here. If anyone 201's listening, we're actually doing the 68, 95, 99.7 rule. And it's just the same as 3. Exactly. It's the absolute value that matters. Great answers, because we're drawing the normal curve on this and saying these points, that is the worst normal I've drawn to date. I won all the prizes with that. It's hard to draw a normal over that. But we'd expect... Guy cannot draw a normal sideways. Last try. That's better. Center's not the center. But it'd be very unusual to have points outside of this bounds right here. Yeah, so these are the unusual bounds for the deleted studentized residual, but then the leverage is like a seesaw. Now, what's really hard for people to get is this is actually the mean of x's. Let me change colors. This is the mean of the x's. High leverage is this point right here. So this is the point at which there's high leverage. So these regions are both high leverage and high deleted studentized residual. Hence why there's the X in these. Anything within X, you will get the row number reported to you for. So wherever you see an X, you will see the row number reported for it. So I wish, that's why I went and looked at the secondary plot. So that is 0.66. It's the highest leverage. That's 66, and that's 463. So 463 and 66. And this plot actually shows us. So you could use some additional. That's 461, and that's that one right there. What is the mean of the x's exactly on a 0 for leverage? Exactly. So something would have no leverage if it's on the mean of the x's. Like for other problems, which I could calculate some leverage and stuff. Just glance. If this works, I'll be so happy. Don't think it'll work. Don't think it'll work. Darn it. Yeah, it doesn't like that. Augment. It's not going to do it. Come on. Doesn't like it. Sad day. I can maybe do it another way. I'll do it here. Give me 2 seconds. This is Brian's 2 minutes right here. 2 minutes with Brian trying some different techniques. Okay. Trying different technique. Doesn't like it. It doesn't have a time order index. Yeah, it won't let me use Fable. It won't let me, yeah, of course Fable's not going to work on it. Fable is for forecasting. I'll take a look at it later. Might have destroyed the data. Let me reload the data. Boop. Reload data. Well, that's a bummer. No worries. Get some cooking done. All right, so that was a little bit of fun from Brian right there. Right out. Oh, we already wrote the full equation, didn't we? Okay, cool. We did that. How many points are influential according to the leverage and deleted studentized criteria? The points that are influential will be the points that we saw back over here. Here we go. Whoops. Where'd it go? There it is. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 points are influential. 9 influential points. The point on the very far right, highest leverage. I think we found that one too, right? run summary on it to get it. Oh, so we're going to investigate this now. Okay, let's just do it. So let's investigate this right here and take a look at it. So this point right here has the highest leverage. So that means it's a very unusual combination of its x's. To look at this to see, can you point them out again? Which the points? There's 1, 2, 3, 4, 5, 6, 7, 8, 9. That represents 1, 2, 3, 4, 5, 6, 7, 8, 9. So the 9 x's, there's a overlap right there. It's hard to see, but that is 2 dots. 1, 2, 3, 4, 5, 6, 7, 8, 9. Those are the 9 points listed right here. This just represents first item in the list. You can see it look kind of crazy if I do this. Now it's going to show more row numbers right there, like row 7. Oh, no worries, no worries. Good questions, good questions. Thank you, Kayla. Let's see why this is unusual now. I'm going to take a look at the product launch data set, and let's go a little wider. Oh, it's a lot more variables than I thought. And then let's take a look at the row. So here's the row, and we have profit. This is a very large profit amount, but we're looking at the leverage on it. It's X1 is kind of higher. It's in the 75th percentile. Its X2 is kind of higher. Its X3 is a little lower. Its X4 is very high. It's near the maximum of X4. Its X5 is kind of lower, and it has a low X6. It might be due to some like low-high combination of it. It's a very kind of on the extremes of most of these. What I'm saying here is X5 is a very low value in the bottom quartile. It's not near the mean of any of the X's. It's very odd. Does that make sense, Kayla? This value right here, because we're talking about this dot, and we're looking at its values. These are the values of this dot. It has extreme values. Like its X5 value is near the minimum. Its X4 value is near the maximum. Its X3 value is, that one's not as usual. That one's closer to the median. Its X2 value is near the maximum. Its X1 value is also nearest to the maximum. And profit is a Y value, which we'd have to look at the miss right there. So kind of unusual. Kind of unusual. And there's that. Question 5. Okay, cool. Got another question right here. Note. Question 5 right here states, fit a simple regression model predicting profit from X2 and run choose order. Oh my gosh. I think we ended last class with this. This is one of my favorites. So let's go right here and make a model predicting profit from X2. And then we have here data equals PL. And take a look. Now choose order. Actually, I don't think we got to this. Choose order shows us a really cool output. I think I love it just because the output's so beautiful. So, Kayla, this one right here is one of those free test questions, I would say. So when we do this right here, here are the steps to ace this every time. Step number 1. Brian's favorite Pixar. No. Step 1. Find highest R squared adjusted. So, Kayla, which order has the highest R squared adjusted right here? Which order has the highest R squared adjusted? Order 1, 2, 3, 4, 5, or 6. Which order has the highest R squared adjusted? That's the first step. Which order has the highest R squared adjusted? All we want to look at is R squared adjusteds and find the highest one. So which order has the highest? There we go. That's the first step done. Step 2, subtract 0.005 from this value. A great thing to put on your cheat sheet, especially the steps. I always like, if you're paying attention, usually I'll like make the answer kind of know, and it's like, wait, he's really pausing on that one right there. But yeah, it's if you see it, I always want people to like say it in their head and like see it, and yeah. So what would we get? We're just going to take this and subtract 0.005 from this, and this is kind of like a value that would be close to it. So this is the value after we subtract 0.005 from it. And then starting at model 1, find the first model that is above this. Okay. So we're going to start at model 1 now. This is usually where people make mistakes. We're going to start at model 1 and find the first R squared adjusted above this. So let me ask you, yes or no, is this above it? is this above it right there? Is this value above it? 0.05, excuse me, is Dr. Petrie's standard. And so Dr. Petrie came up with this idea. It kind of matches AICC, you'll notice here in a moment. But Petrie came up with it as something that is pretty close to our R squared adjusted. Like, it's kind of close to it, and it says, well, we want to use simpler models. So the goal of checking the smaller models is to see if we could use one that's a little bit simpler, to be like, well, these are basically the same. So these are basically the same, so let's use a simpler one, because the line is the simplest relationship. And this does not meet our standard. Do you see how the line sticks out like a sore thumb? This is 41% explained, but these have, well, not quite R squared, but this is 40.41% R squared adjusted, where these are closer to 50. How about the second one? Does that meet our standard? Does this second one, where we start from the first, does the second one meet our standard? Does the second one meet our standard for we have to be above that value? Does the second one meet our standard? So we look at this and we say, is this above this value? And that means it meets our standard. Yes, Sierra, great job. And that means that's the right order to use. You stop right there. You don't continue. The whole reason with checking model 1 again is to make sure, great job, Kayla, right there, and Sierra. The whole reason with checking model 1 is to say, could we just use a line? Do you see how the line really doesn't do as good of a job as these other ones? But the other ones all look very what? Like, look at the R-squareds adjusteds on these, and then look at the models visually. They all look pretty what? So look at the R-squareds adjusteds. They all look pretty this. And then look at the lines themselves. They all look very what? Hence why it's like, well, then let's just use this one instead. Like, you're having a hard time running arguments. Oh, make sure to hit the enter at the bottom. Carson, thank you for asking. They're all curved, and they're all basically like a parabola, right? They all kind of wrap into one parabola. So if they all kind of look like a parabola, why go to a seventh order relationship? Let's just use the second order. So Carson, make sure, try going down here to the bottom and hit enter, 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 enter. Does that help out, Carson? Give that a try right there, and we'll make Carson a mod right here. Comment like that, I'm pretty sure you're a student of ours. So try going down there to the bottom and go enter, 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 and you might have it showing below the chunk, like it might be down here below it, and that's where you'll see the output. So try hitting enter, that should fix it, and you just want to go to the console and go boop, 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 boop. Because when you run the C interactions, you'll have to go here and go boop, 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 boop. You have to do that, because it'll, there you go. Hopefully that helped out. Carson, let me know if that didn't help you out. Good, Carson, thank you for being here. Good questions. Fit the model, predicting profit with all the interactions. Include the relevant polynomial terms in the PL data frame. See the slide. Which one are we doing? Fit the model, predicting profit with all interactions. And include the relevant polynomial term in X2. Wait, what? Oh, and include the polynomial term. Oh, man. Man. Awesome, Carson. Good to hear that. Okay. So what we have to do, we got to go here and go M, save into LM, profit. We're going to go here and include all the interactions and then do a poly. No. Got to go plus poly. And we're going X2, and that's the X we're calling, and we're doing to the second order. And that should do it. Data equals PL. There we go. Let's see if it ran it. And we do. Ooh. Oh, because it... Excuse me. This right here means we've included the variable twice. There's actually complete multicollinearity. Because we included x2 here, when it tried to include the simple x2 coefficient, which would be the linear term, it was already included here. So we're getting NAs. It just couldn't add it. Makes sense. It's complete multicollinearity. Because you already have x2 in the model, you're adding x2. The collinear relationship between them is 100%. So the model actually can't estimate any coefficients if you try to add it a second time. Now, the polynomial term for x2 can get estimates and does add new information. So that's super cool right here. With every bit of interaction in here, the polynomial term is actually adding a lot of significant information. So the polynomial term was a good thing to do. R squared adjusted looks to have gone up too, so we're good on that. Is the highest polynomial term statistically significant? Oh, yeah. Definitely. Right here. Good stuff. Has the model improved in its values? I think, yeah. The model looks to have improved because if you look at the R-squared adjusted from our previous models, I think we have just the interaction model right here. And there, oh yeah, it's gone up a lot. That was, for one variable doing that, for the R-squared adjusted, pretty good stuff right there. The RMSE previously was this 0.2729, and now it's 0.2669. So a little bit better. So the RMSE, the typical miss, has increased, or decreased, excuse me. The R-squared adjusted has increased. You want these to go up, especially R-squared adjusted. You want your RMSE, your typical miss, to go down. So the model is missing less on average, and the model is doing better comparatively on a fair comparison via R-squared adjusted. Make sure to use R-squared adjusted. Very important right there. Now we got a little bit of variable creation. I think it's we got two more. Yeah, we'll do two more here. Question number 6 looks to be variable creation. What is it? On the products on CNN and Fox News. So here we go on Hotel. Question 6. Imagine X5 and X3 represent the number of advertisements on CNN and Fox News. There are 2 sites, and we can do this. Then the variable X1 represents, or this combination, so find this new variable. Let's do it and call it PPA. So what we're going to do is we're going to take, we have to put PL before these, and create this variable. So now we've literally created a variable. So this is what is called variable creation right here. Variable creation can be anything you want. We could have multiplied these together. Now don't do this, but you could do anything you want. You could, I don't know, multiply them all, and then you could do that. Oh, it's mad, integer overflow, NAs, we don't like that. So you can do anything you want as long as it's mathematically possible. The equation tells us to do this right here and create this new combination variable. Now, a lot of times I like to take these variables and add them to my data frame, and what will happen here is they'll be appended to the very end of your data frame. We'll do a limited output, or we'll just view it. And so now we've added it onto the data frame there, the variable PPA. If you store to a spot in a data frame that does not exist, you create that spot in the data frame. Now, what's really great about this is we can fit a model predicting profit from this variable. So y tilde x comma data equals, we get that down so well. And there's the new variable. Remember, we had to add it, and there's our model. And let's see how the model did. Did the model do great? The answer is, well, it is statistically significant, but it's only 2% of the variation explained. Now, if that's stocks, that might be super cool, but this is profit. Something tells me my company probably wants us to be explaining more than 2% of profit, of the variation in profit, rather. And also, our typical miss is much higher of 0.51. Although the relationship that PPA has with profit is statistically significant, the model itself looks to carry much less practical significance, denoted by the R-squared of less than 2% of the variation explained in profit by the variable PPA, along with the typical miss of the model being 0.51 billions of dollars, something like that. We're missing typically by a much larger amount compared to our other models. That was a good one. It can be difficult to tell if a prediction requires extrapolation. Extrapolation is when we predict... Oh, I need to put timestamp. We're started. That was a quick one. Well, darn it, I just did that one in 2 minutes. I think variable creation is so open-ended. Well, the thing about variable creation is it's so open-ended that you could create any variable you want. As the notes say, you need domain knowledge to create variables. You need some understanding of what variables are you combining together to create your new variable. So this was maybe not the best of ideas. Someone said, hey, let's take x1 and divide it by the sum of x3 over plus x5. And we're like, sure, why not? And then it's like, that didn't really work. And that's what can happen. We could have added it to our model too. Let's go over here. Now that we have it, and oh, it's interacting. It's probably because it's composite. It's not significant. I wanted to, yeah, Gia, great to see you here. We're on the last question. If you have questions, let me know. We're on the last question, which is extrapolation, which is when we make predictions outside the bounds of our x's. So it's difficult in multiple regression to tell when are we outside the bounds of our x's, because now there's more x's to care about than just one x. So the way we can look at this is we have to use the code extrapolation check. So it's already got the data frame in here, and we have possible combinations of x's. So, oh no, I didn't break my interaction model, did I? Now, what do these represent? And I'll show you something here, Kayla, in a second, and Gia and Sierra. So, what do these represent? If you think about our x's as a cloud of space, so it'd be very hard to draw the multivariate sense, but it might look something like this. That value right there at the center, this red dot is meant to represent what in a multivariate? If you think of like a 2x space, that red dot right there would represent the what? That red dot would represent the what? What would that red dot represent? The mean of both x's, right? So that's the mean in the multivariate space. Great job right there, Kayla. That is the mean of both x's. So that is where the mean of x1 is, the mean of x2 is. And so then we'd have to ask, let me give you 2 points right here. A yellow point and a blue point. Which of those points is more of an extrapolation in our x space? Which of those points is more of an extrapolation in our x space? So which of those points right there is more of an extrapolation in our x space? The yellow or the blue? The yellow. But isn't blue further away from the center? And this is where we don't have to do the high-level mathematics. It breaks down, as we mentioned in class, to things like eigenvectors and eigenvalues. Because the vector space, yellow is further away in terms of like vector degree. If you draw the vector space of this, which would be an orthogonal sort of plane. So the blue is literally further away. But in terms of like, imagine this is okay, think of it this way. This is a good way to think about it. If I have a confetti balloon and the confetti balloon explodes right here. So you're at the center. I'm like, hey everybody, confetti, woo! Which person right here is going to get more confetti on them? This is the confetti that flies out. I go, woo! Here's Brian here at the center. Confetti everywhere. Who gets more confetti on them? Person yellow or person blue? Who gets more confetti on them? Because it's where the x's and the way they are related is just the variables. The blue, right? But wouldn't you say the yellow is closer? The blue gets more confetti on them because that's where they were going to like that out. So the yellow doesn't get any confetti. They're outside of the X space. They're outside of the dots. But the blue is inside of it right here. But isn't the yellow like mathematically closer? It is. It's mathematically closer. Ah, Gia, great job right there, Gia. Great work seeing it. So the issue we get into is the way in which these X variables are related. It's going to be very hard in a multivariate sense to say in what way would we be outside our X space. Now, I want you to see something. No, want that. Watch this. If I were to take this value, oops, I grabbed the wrong one first. Dang it. There we go. What value am I putting in for all my x's? The first value of x being tested right here is the what for it. The first value being tested now in my new version of this is the what. I'm saying, let's look at this one. The first value is the what. Take a look right there. The first value is the what for this x. So the first value is the mean. So the question becomes, how far are you away from Brian's confetti explosion right here? And when you think about this, if you are Brian, how far are you away in terms of 100% outside of it? You're 80% outside of it. If you are Brian at the mean, what percent outside of it would you be? Because this is the point I'm checking right now. I'm checking this point. If you are Brian, what percent outside of it are you? Outside of this X space, if you're the mean of the X's. You'd be 0%. Mm-hmm. So if we rerun the code right now and we do the extrapolation check on it, it's 0. And that's what that represents right there. That is the red point. We now input the means, and this point right here, 0.2, is at the 98.6th percentile. Like, if we could visually see it, it would probably look something. See, I can't even grab it. Really? It would probably look something like that. That's the second point. Does that make sense? Like, the second point is still within our X space, but it's towards the outer edge of it. Like, it's towards the outer edge of, like, terms of degree of farness from the mean the points are. So it is a bit of an extrapolation, I would say. So that second point, that is Brian, who's at the center, has a value of 0 for extrapolation check. And the other point has a value of 98.6, meaning in the terms of the X space degree outside of it. And probably that point would have a lot of leverage too. At least this is a new point. Extrapolation deals more with new points being predicted, but a point at this in our model would have a lot of leverage because it's very unusual in its X space. But that's got it. Any other last questions? This was a really good activity. A lot of good work, a lot of serious, a lot of work. But yeah, what are people thinking? We'll go back to the main screen. Woo! Got the big presentation. Check this out, Kayla. And everyone, tell me what you think of this. I'll show you it right here. Actually, you know what? I'll send you the form too. If you're watching this, you can fill out the form. I've gotten 91 responses, and I'm gonna probably talk about this a little bit. I asked people in my 201 classes. I thought of this day. I was like, it'd be good to ask this. I asked, what do you think about online education? What do you like? What do you not like? And so this is my presentation for tomorrow. We got down here Mubot at the end of this, but this is what I'll be going over. I got some cool tricks I'm going to do. I was making some new... We like to say fire chat. Where is it? What if I pull it up? Here we go. Here it is. Here's the fire chat. Online chat. Fire chat. Yeah, so making new screens that I got to implement tonight. Points, the point system. We start about the point system. Here's the point system here. I was making these last night. Watch me misspell symposium. It's the UT Online Symposium. I'm going to be talking about online education and adding music, which we're doing right now, as you can tell. I didn't find something as good for this one. I was going to make it like blink, and I was afraid I was going to give people like a seizure or something. Yeah, so I was working with After Effects on this last night. I don't know, I've learned so many random things. I was like, let's include Mubot on this. I'm gonna do some stuff. But I wanted to make this look really nice. 7 years online teaching. I like double checked and I was like, oh, I better make sure it's like 7 years. Might be 8. And I was like, okay, I can find emails going back 7 years on online teaching. So I've done it for at least 7. But yeah. Gosh, that picture's 3 years old of me now. I was just but a young lad. Yeah, no, well, thank you. I want people to know these things, and I'm finishing up my presentation on it, so I'm gonna be doing that in the morning. Oh, thank you, Kayla. That's really kind of you. You know, it's about, fill out the form if you want. I hope others join in too. I'm always happy that, people come back and watch the videos. Everyone has a different learning style. We have a lot of silence, and I think, don't go to teaching Reddits. People are so negative on those. They're like, don't trust your students. Don't talk to your students. Don't ever. And I'm like, well, we have a certain relationship with our students. We're teachers. My whole family. I want to be a positive influence on people's life. I want people to enjoy class. I want them to have a good time. I want them to be like, yeah, it's class time. My whole teaching philosophy goes to the last day of class we had growing up. Do you remember that last day of class in 3rd grade, Kayla? Maybe 2nd, 3rd, 4th grade? What was the last day of class? Because I always loved it. Last day of class was the best day of class. If it was the last day of school, I was so excited to go in 3rd grade. It wasn't always that way, like senior year of high school. Well, that was interesting. It's like, I'm going to college. Gosh, I just had that feeling. You get a weird feeling when it's like, I'm going to college. A whole new adventure in life. Party, exactly. And so, right there, give some points out. So I started to realize this when I was teaching. And I might even do an exercise tomorrow to say, like, if you think about, I think more educators need to say, what did I want when I was a student? And I want to be, not that I'm here to like entertain, but to a certain degree I am. But a lot of people in their comments to me, I was reading the comments from the first class, were like, online class is so boring. Like, I'm just watching someone read slides, which is a common complaint of many courses. I read so many things on so many things. But people don't want to be bored. They, if you're going to be in class, you want to have a good time. You want to see friends. That's a fun thing about going to campus. It's like, I'm going to go to campus, get me some Starbucks, walk into class, sit next to my friend, take a trip across campus, see the gardens or something like that. Hey, it's exciting. And then if you go to the online class, you're like, I'm just going to sit here and listen to someone lecture and have my camera on and they're going to stare at me. And they're like, I don't want to do this. So I want them to think about what they liked. Exactly. And that's the whole point is this is a lot of what I do, which I don't think people reward wrong answers enough. That's why I like to have sayings like, we get it wrong in class to get it right on the test. So, yeah. Oh, Kayla, you're super smart, Kayla, and you've done great. And I'm so excited to hear about the future things you'll be doing. Kayla, JD right there. Super excited to hear about that. So I know you're going to do great. I think a lot of people do things like pulling the chat. A lot of people don't keep up with chat. Like, chat's not going to talk to you if you don't talk to them. If you don't read what chat says, they're not going to talk to you. Why talk to you, teacher, if no one's reading it? What's the point of that? Like, and then if you do a wrong answer and the teacher's like, no, that's wrong. And then you're like, whoops, man, not answering questions again. During class, I'll let silence ride. During office hours, I've decided that I'll answer questions because I realize a lot of people go back and watch the videos. But if I have enough people, I'll get some answers. And I think they should wrong. Like Dr. Cox on Scrubs, like wrong. You're wrong. Start doing that, students. But yeah, it's fun to use music and everything. I don't know. Hopefully people find it very beneficial. But I was up late last night working on this. Hopefully it looks good. Found a nice template. I obviously didn't make. I was like, "Ooh, this looks good." Spent like 30 minutes to an hour looking for a template, and then made my template on it. Like how do I optimize this space? So that's got it. I'm going to be preparing my lecture. It's getting some final touches on it. And I'll be back here tomorrow for 320, 475, and office hours. Bye for now, everyone. Bye, Kayla. Have a great dinner. Enjoy. Woo! Bye, Kayla's family. I'm back. Hey, Barrett, what's up? What do you need? What are you working on, Barrett? No, you're not too late, Barrett. Barrett, you still here? Barrett. What you got, Barrett? Already played that one. Oh, dude. Don't tell me we lost him. Barrett. Okay, cool. What you got? Bye. What you working on, Barrett? You're 201. And which one we working on? Let's take a look. We'll throw it in here at the end. What you got? We'll see. I think he's writing out the problem probably. Thank you, Barrett, for being here. 100 points. I was literally like a button or two away, Barrett. Perfect time. Let's see what Barrett says. What do I use if I need to predict what two numbers? Oh wait. Oh, is this the nearsightedness? Is this the nearsightedness of the children? Nearsighted children problem, right? Access denied. We can't do anymore. Let me reload my Pearson. If you hang out on my Pearson too long, it gets mad at you. I'm pretty sure this is nearsighted children problem. Nearsightedness of children. It'll be 3 standard deviations. Take the proportion of the 3 standard deviations and times it by the sample size. I'll show it here in a second. Pretty sure it's nearsighted children problem. Because I'm nearsighted and I know it. Yep. So make sure to do 3 standard deviations. And here, I'll show you right here. So we do meet the conditions. We assume random 10% success failure. Well, don't just assume them. They can be checked. And so this is the sampling distribution right here. The sampling distribution will have a mean of 12%. So that narrows it down to answers B and D. Ah, yes. Do 3 standard deviations. And so we go P times Q over N square root. And so the standard deviation looks to be, and this is 3 standard deviations right here. 12 would be at the center because that is mu p hat equals p. And then 3 standard deviations is going to be, we times this by 3. We can see 12 plus 7% is that, and 12 minus 7% is about that. So that should be it right there. And then this graphic kind of clues in on what we would use right here. Because if you notice, the graphic goes 3 standard deviations. So we can use about 4.8%. So this is the lower end of what we would expect, and times it by the 176. And we'll see the lower number here of 8. And then if we take the higher number, which is 3 standard deviations, do note that this is 3 standard deviations. The 3 standard deviations up of 1.92 times 176 is going to be rounded to 34, and that's got it. How's it look, Barrett? Let me know if you have questions. Is there anything else you're wondering about? But good work, Barrett. Good job practicing. These are tougher problems. You're welcome. No, you're fine. Barrett, don't worry. Barrett, I want to throw you some 500 points. Barrett, this is what it's all about. I want people to hop in here and ask their questions. I'm glad you were here, just checking out the end of this. And if I'm here, I'm ready to answer questions. Everyone knows I hop around to some Discords and emails, and I appreciate everyone who always knows I always take a break or something. I might go eat some soup or some yogurt or something, get some food. And no one's ever been like, you didn't reply to me quick enough. Maybe someone thought that. I'd say, I'm sorry. I need a haircut. I'm getting married. I need a haircut. My hair's been so crazy lately. I need campus cuts by Monica. We need to fly her out to Texas to get a haircut for the wedding. And then I'll have right hair. It's looking crazy. Shout outs to Campus Cuts by Monica. You've got it. Awesome. Well, I'm going to go grab some food here. Until then, we'll be back tomorrow. Great work, Barrett. Keep up the great work. Bye for now, everyone. Bye.